right, so the only topic that we're going to get into today is from chapter 21. And the topic in chapter 21 is all about nuclear chemistry. And so what we'll be getting to as far as nuclear chemistry is concerned is we'll be talking about some of the basics and some of the kind of ways that you can, why we focus on nuclear chemistry, where do we see it applied most often, and then we can get into some of the other stuff like tracking its reactions and looking at nuclear stability and that kind of stuff. And so to that end, we're going to start by talking about radioactivity, because really the study of nuclear chemistry comes down to a look at radioactivity. Now, we talked a little bit about radioactivity in chapter 2. In chapter 2, we focused on the idea of nuclear radioactivity from the standpoint of how it was used to discover certain parts of the atom. Because radioactivity is the spontaneous emission of energy from an atom. And when that atom releases that spontaneous energy, what you get is a change in the nucleus itself. And so we largely credit Becquerel with discovering radioactivity using a mineral known as pitchblende. We also can talk about Ernst Rutherford. That was our primary focus in chapter 2, how he used alpha radiation to discover the nucleus. And then we can also talk about the Curies, who are credited with discovering polonium and radium as elements. Now, radioactivity is directly correlated to another concept known as nuclear stability. And in nuclear stability, what we have to understand is that other than hydrogen atom, where we have just the one proton and usually no neutrons, other than that, we're going to have some repulsions occurring in that nucleus, wherein we've got positively charged particles all really close together. And we know that like forces repel each other. And so we know that as soon as we go from hydrogen to helium, we're going to see some repulsion taking place inside that nucleus. Now, we also know that neutrons play a pretty key role in stabilizing the nucleus and making it so that the nucleus is not going to just fly apart into a bunch of different individual particles. And so when it comes to looking at stability, we often will look at the ratio of neutrons to protons and the how many neutrons do I have per proton. And that is going to be a considerable factor in the matter. And to that end, what we end up talking about is something called the belt of stability. Now, the belt of stability is just a graph. On the graph, we will have protons on one of the axes, and we will have the number of neutrons on the other axis. And so you've got these two axes here, and what we're going to see is we're going to get a graph that shows all of these different isotopes that exist. There will be a band of them, or a belt, that are stable, and then there will be another band or belt that are unstable. And so whether an isotope is in the belt of stability or outside of the belt largely depends on the ratio of neutrons to protons. For light elements, and this is elements where our atomic number is less than 20, that ratio is about 1 to 1. For elements where my atomic number is greater than 20, got that backwards here. We start to see that in this particular case that the heavier elements are going to require more neutrons to stabilize it. Outside of the belt of stability, we can refer to isotopes as either being neutron rich or neutron poor. The neutron rich ones are the ones that have too many neutrons and are unstable because of that. The neutron poor ones are the ones that have too few neutrons and are unstable because of that. And so from that aspect, we can start to look at what the belt of stability actually tells us. And so this is the actual graph of the belt of stability. And we can see here that all of the black dots represent stable nuclei. All of the yellow dots represent the unstable nuclei. And this red line represents a pure 1-to-1 ratio of protons and neutrons. And so you can see that up until about element number 20, calcium, we spend most of the time at or pretty close to the line. Once we hit calcium, though, we start to see that it bends up. And so by the time we hit iron, element number 26, the neutron ratio is about 1.15 neutrons for every proton. By the time we hit iodine, we see that it's up to about 1.4 neutrons for every proton. And by the time we get up to bismuth, element number 83, it's up to 1.52 neutrons per every proton. Now notice that after bismuth, all of the dots, all of the nuclei here are unstable. We have no stable nuclei after bismuth, element number 83. So that's an important thing to note. And the reason why that's important is that says that bismuth is the last stable nucleus. Everything after bismuth is radioactive in some kind of way and is unstable. That doesn't mean that it's not naturally occurring. That just means that if we find it, it is unstable. It is radioactive. And so in here are a good chunk of your rare earth metals. You have all of your transuranium. You have all of the synthetics other than technetium. Technetium, if you look closely, you can see there is a spot here where there are no black dots, and that corresponds to technetium. Technetium element number 43 is completely absent of any stable nuclei. It's completely unstable. All of its isotopes are radioactive, and you can see that we've got quite a few dots in there. So there are many known isotopes of technetium, but none of them are stable. And after bismuth, none of these are stable either. So in there, you've got your poloniums, you've got your radons, you've got your radiums, you've got your uranium, your newtonium, your neptunium, your plutonium, and all of the others that would come after that, including all of the most recent ones that fill us up to element number 118, oganesson. So the question I'll pose to you then is this. We've talked about the idea that there is a degree of stability and that there is a relationship between the proton and neutron ratio and stability. But what I'm going to ask is a more fundamental question than that. What holds the nucleus together? Why doesn't the nucleus fly apart especially when we get into some of those heavier atoms that have so many more protons? You've got all those protons in a really tight confined space. Why don't they break apart? Why don't they fly apart and just stay separate?
I'm guessing because there's like something that holds it together. Like when we were talking about like intermolecular forces, but not intermolecular forces, because I don't think that applies. Because I think that applies to like compounds rather than just a single nucleus that's that small.
Okay, yes. So you're right. Intermolecular forces are forces that exist between molecules. We would be talking about an interatomic force, so to speak, as opposed to an intermolecular or intramolecular kind of force. So, yes, we need to think about there's some kind of internal force that's holding it together, and that internal force is something called strong nuclear force. Strong nuclear force is a fundamental force of nature. It helps keep the quarks together, the subatomic particles that make up our protons and neutrons and electrons, and helps to keep them together in the nucleus itself. And so what we can talk about in that perspective is an idea of something called binding energy. And in fact, binding energy is a synonym for strong nuclear force. So strong nuclear force is the force that holds it together. Nuclear binding energy is the energetic force that we associate with it. And to that end, we can see on the graph here that what's interesting is that all atoms have strong nuclear force inside of them, even the ones that are radioactive. So if I look at uranium 235 and 238 here at the end, those are still held together by strong nuclear force. And that's what keeps the atom together as a whole. But what we'll see is that if we look closely at the relationships here, the one that is the most stable, the one that has the strongest nuclear binding energy, is actually this particular isotope of iron 56. So much so that if we're looking in the long kind of scheme of things, every atom, every element is seeking to get to that spot, to get to that iron 56 isotope. And on this side of the ledger, if it's possible, atoms will go through fusion processes where they will stick small atoms together to make larger atoms in an attempt to get up to that most stable spot. And on this side of the ledger, fission will occur where the atom literally rips apart to try to get to that most stable spot. Now, these processes, fission and fusion, are not processes that happen naturally anywhere other than places like outer space, stars, high pressure kinds of situations, maybe perhaps deep within the Earth or within a large planet. For the most part, once they escape their solar origins, they have a very hard time actually going to and getting to that state. But if they do stay in the star, if you know anything about stellar evolution, what happens is as stars begin to burn through their hydrogen, they will go through a series of changes and they'll start burning through helium, they'll start burning through lithium, they'll start burning through, whatever elements have been interconverted inside of the core of that star. And one of the last stages of a star is that it has an iron center. If it's able to last that long without blowing up. So, as I said before, nuclear binding energy is our method for determining the stability of a nucleus. And the way that we calculate binding energy is with a relatively familiar equation. Now, you may not have seen it written this way. You might have seen it written in its more familiar kind of format. E is equal to mc squared. So that famous equation, E is equal to mc squared, the one that anyone who thinks and tries to sound smart will immediately spout off as a sign that they are smart. What that is referring to, that particular equation is referring to the nuclear binding energy associated with a nucleus. And it's the amount of energy that holds together the nucleus as a whole. Now, the E there is our binding energy, the total amount of energy that is being used as the strong nuclear force to hold together that nucleus. The M is actually a delta M being a mass defect, the change in the mass of the nucleus. And where that comes from is, if you've ever looked real close and taken the atomic mass of really any kind of atom and compared it directly to the actual masses of the protons and neutrons that make up that nucleus, what you will find is that the atomic mass is always less than the mass of the nucleons that put it together. And the mass difference is what we call mass defect. So mass defect comes from that characteristic of the nucleus as it comes together. So delta M is the mass defect, and then c squared is the speed of light squared. And so if we look at it from this perspective, we can see, for example, that helium is a relatively simple nucleus. It's got 2 protons, it's got 2 neutrons. Relatively simple and straightforward. If I take the masses of those 2 objects and add them together, so I've got 1.673 times 10 to the negative 27th times 2 plus 1.675 times 10 to the negative 27th times 2 what I end up getting is a total mass of 6.696 times 10 to the excuse me, times 10 to the negative 27th.
And you just multiply 2 by each of those numbers.
Yeah. So that's the total mass of the 4 nucleons. Now, the mass of a helium-4 nucleus in kilograms would be 4.003 divided by Avogadro's number. And then divide by 1,000 to get kilograms. So it would be it's 6.647 times 10 to the negative 27th.
Is that one just helium and not helium-4?
That
For that.
I'm estimating, but it would be, it'd probably be a little bit smaller than this.
Okay, so that's just for the
I
helium
don't have that.
itself, right?
I don't have the, yeah, that's the helium itself.
Okay.
I don't have the actual atomic mass of helium-4 in front of me. But nonetheless, the mass defect here would then be just the difference between them, 6.696. Minus 6.647. Which would be 4.9 times 10 to the negative 29th. So we're not talking about a whole lot of mass here, but if we take that and multiply that by the speed of light squared, we would get a relatively significant amount of energy on the atomic level. Certainly if we're talking about moles or other quantities that are certainly larger than one atom, we're talking about not an insignificant amount of energy. And so this is what holds together that nucleus. And so you could do this for any atom. If you knew its atomic mass in AMUs or in kilograms, all you'd have to do is just multiply and add. So like I said, all I did was I had 2 protons, so I took this one times 2. I had 2 neutrons, so I took this one times 2. And then I added them together. to get this mass here. And then I estimated the mass of the helium nucleus from the periodic table. Again, that's not completely accurate. It's probably a little bit lower than this, but nonetheless, it's pretty close. And the process is really what's important there. So do you have any questions about mass defect?
Mm-mm.
All right. So what happens when we have radioactivity then? Well, when radioactivity occurs, that's the result of something called a radioactive decay. And what's happening there is an unstable nucleus is more or less starting to fall apart. And as it falls apart, it releases energy and it releases particles. And these particles get ejected out of the nucleus in an attempt to stabilize the nucleus. Now, the type of radioactive decay that we see really depends upon the mode in which the nucleus is existing. Is it neutron rich? Is it neutron poor? And how is it just too heavy in general? And so what we see there often depends upon what the nucleus looks like at the time. And so there are four primary types of decay. There's the alpha decay, the beta decay, the positron emission, and the electron capture. So we'll go through each one of these in turn. Now, before we go through them, we're going to track the results of those decays using transmutation reactions. And I referred to this a little bit on Friday. These are the ones that involve relatively simple adding and subtracting. Because in a transmutation reaction, what we're doing is we're tracking, here is our parent nucleus, here's what we started with. This thing was unstable. It went through some kind of transformation. And in its transformation, it splits into a daughter nucleus and a particle. And that particle is the thing that is what names the radioactive decay, whether we get an alpha particle, a beta particle, a positron, or an electron capture. And the daughter nucleus is what's left over after that transformation occurs. Now, transmutation reactions are a little bit different than what we've seen in our other types of balancing. In balancing transmutation reactions, we're not interested in conserving atoms. We're not really even interested in conserving nucleons necessarily. We are interested in conserving total mass. And to do that, what we have to understand is that we can split this equation in half. And on one side, we're going to have the reaction itself and all the reactants over here, and the sum of all the mass numbers over here, and sum of all the atomic numbers over here have to match the sum of the mass numbers over here and the sum of the atomic numbers over here. And so that's what we're really looking to conserve in these kinds of reactions. We're interested in conserving total mass number, and total charge in the sense of atomic number. So a little bit different than what we've been doing in the past, but not such a huge departure that it really doesn't make any sense. So let's take a look at these. Our first type of decay is alpha decay. Alpha decays tend to occur most often when we have more massive nuclei that need to ditch their extra weight. So we tend to see this the most often when our atomic number is greater than 83. So when we have things that are greater than our most stable, our last stable nucleus, than our bismuth, alpha decay tends to dominate those kinds of reactions. That's not to say that the other types of reactions aren't going to occur at those high weights. It's just to say that alpha is the most common among those. And it's not to say that alpha decay doesn't occur at lower weights. It's just less likely to occur there. So alpha decay is when a nuclear reaction emits this unstable nucleus that gives us an alpha particle. The alpha particle is this one right here. Alpha particles are massive radioactive particles. What you have is a nucleus that has 2 protons and 2 neutrons. So in a lot of ways, it's very similar to a helium nucleus. Primary difference between an alpha particle and a helium is that the alpha particle has no electrons, whereas helium usually will have 2. But in terms of the transmutation reaction, let me show you what I was talking about there. So again, we can split our equation in half, and we can see that for the atomic number, I had 92 for uranium, and if I add together the 2 in the alpha particle and the 90 in the thorium, I get 92 down here as well. And similarly, I started with 238 nuclear particles here in uranium, and when I add together the 4 in the alpha particle and the 234 here in the thorium, I get 238 there as well. So if you find yourself in a situation where you are missing a particle or missing the nucleus, the daughter nuclide, all that you really need to do to solve the problem is subtract. 238 minus 4 would have given me the mass number of 234. 92 minus 2 would have given me the atomic number of 90. I could look at the periodic table. Element number 90 is thorium. I could have come up with the answer that way. Now, in beta processes, what we see, these tend to in beta decay, we will see that it occurs in all values of atomic number. Every isotope is capable of undergoing beta decay, but it's the most common when we have less than 83 protons and we have a neutron-rich nucleus. So if we think about that band of stability, neutron-rich areas would be those above that band of stability where we've got too many neutrons and not enough protons. And so what happens essentially is that we turn a neutron into a proton. That's essentially what happens in a beta decay. A neutron turns into a proton, and it does so by, if we can think of a neutron as being kind of packed with these small amounts of negative and positive charge. If I have a neutron that has equal amounts of that negative and positive charge, and we ditch one of those negatives, then the extra positive charge would shine through. And that's essentially how this all ultimately works. So in beta decay, we see a neutron turn into a proton, and in the process, we end up getting a more even ratio of protons and neutrons. So if we think about this, we had 8 neutrons and 6 protons at the beginning. our daughter nucleus has 7 neutrons and 7 protons. So it has evened up. And at this low of an atomic number, that's an important characteristic. Beta particles, we can always pick them out. Beta particles have no mass, -1 charge. We can kind of think of them as nuclear electrons. So very similar to electrons. Sometimes we refer to them as electrons, but they're not truly electrons. They're negative subatomic particles that tend to exist in the nucleus, as opposed to electrons, which are subatomic particles that exist outside of the nucleus. Any questions so far?
No.
Now, in the case of many of these types of radioactive decays, what we tend to see is that it is rarely the case that one decay is significant enough to get an atom that is unstable to become stable all of a sudden. What we usually see is that these occur in a series of decays. So let's take uranium-238, for example. Uranium-238 starts up here, atomic number 92, and in the end, uranium-238 will probably decay down to a more stable form of lead-206. But to get there, we're going to see it goes through a series of alpha decays, then beta decays. Then here's a series of alpha decays, then a series of beta decays, then an alpha decay, then some beta decays, then an alpha decay. And so it could take, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 nuclear processes, maybe even more sometimes, to go from an unstable isotope to a stable one. And so that's what we mean by a decay series, is that just because something undergoes a decay doesn't mean that it's immediately stable after that. It's more stable. The radioactive decay has made the isotope more stable than it was, but that doesn't necessarily mean that it is stable enough to quit being radioactive. Now, these processes can take thousands of years. These processes can take less than a second. It depends upon the process itself in terms of how long each one of these steps take. So even though uranium-238 will eventually make its way down to lead-206, that process could take tens of thousands of years depending upon the route taken and how long it takes for those decays to actually occur. Because just because something is radioactive doesn't mean that all of its samples spontaneously decays all at once together. Samples usually are kind of random in their decay, and an entire block sample could take quite a while to actually decay along those lines. Okay, third type of radioactive decay is something called positron emission. In positron emission, what we have is kind of similar to beta decay, only the opposite. So instead of a neutron giving up a negative charge and becoming a positive charge, What we see instead is that we have a proton that gives up its positive charge and in the process becomes neutral. And so what we see in this kind of scenario is a proton converts to a neutron. And again, this is most common when our atomic numbers are small. Net result is a proton converts into a neutron, and we end up getting this positively charged particle coming out on the end. Now, positrons are essentially the antimatter analog of electrons. So a proton and electron have the same mass but opposite charges. Finally, we have electron capture. And in electron capture, what we get, these same notes actually can apply for this as well. It's common among small things. We get a proton converting into a neutron. The difference is instead of an emission of energy, an emission of particle, what we get is the absorption of a core electron. And so the carbon in this case grabs one of its inner electrons. The proton basically becomes annihilated by that electron and it becomes a neutron. And we get the same kind of effect. There's still radiation outpouring, but there's no particle associated with it. But in terms of transmutation reactions, we can treat them in the very same manner as before. All of the mass numbers add up. So 11 plus 0 on the reactant side equals 11 on the product side. 6 plus -1 gives us the 5 on the product side, which is how we determine that it's boron.